Resume recording. Let's continue. Okay, good. Anyway.
I have my notes here, so I will be referring to them. All right, ready?
Okay, let's start.
Okay. Yeah, so my presentation today is going to be on stellar evolution, or the life cycle of stars. This is a bulk color image of the pillars of creation by JWST that happened back in January. So really cool image, but let's get into it. Yeah. This
Everything.
Yeah, okay. I'll just do the mouse. Okay. All right, so what is a star, right? A star is an astronomical object comprising of luminous spheroid of plasma held together by its gravity, right? It's just a fancy way of saying it's a hot ball of gas. There's approximately between 10 to the 22 to 10 to the 24 stars in the observable universe, and they do come in a wide variety, mostly based on their mass. That will generally change how they are observed. They're powered by nuclear fusion, so they generate energy by combining lighter elements to heavier elements, and generally stars have about 4 phases in their life. We're going to first talk about the anatomy of a star, right? So all stars generally will have these kind of layers. This is a general case. Generally, they'll have a core in which nuclear fusion is taking place. And then you'll have these radiative and convection zones outside as energy is transferred from that core, from that nuclear fusion out, and is released as heat and light. Yeah. So stars are powered by something called stellar nucleosynthesis. It's a fancy way of saying fusion. I have to let people.
Yeah,
I have to let people in. Okay. All right. You can all come in. You're all invited. Okay. Yeah. Let's get going. All right. So stellar nucleosynthesis, or fancy word for fusion, is basically where stars get their energy from. You can think of it as E equals mc squared, or a relationship of mass and energy, where mass is converted into energy. For fusion reactions, it's generally about 0.7% of mass is converted to energy, and that energy is released as positrons, neutrinos, and gamma rays. So yeah, this is the main branch. This is how most stars generally will undergo fusion. It's called the proton-proton one branch reaction, or chain reaction. Basically, you take your 4 protons and you'll combine them to form helium, is the output. There are other pathways, both in the proton-proton branch pathways as well as heavier elements, all the way up to iron. All right. So these are the other pathways. As you can see, again, 4 protons come in, you get your helium out, or 4 protons per helium. There's also additional pathways. This one's the CNO cycle, or carbon, nitrogen, oxygen cycle, where basically carbon acts as a catalyst, and again, converts hydrogen to helium. There's also other methods or other processes to convert heavier elements like triple alpha, where you have 3 helium nuclei coming together to form carbon, as well as heavier stars will go into things like carbon, neon, oxygen, and silicon burning, where basically you're fusing a variety of ways, fusing to heavier and heavier elements until you get to the nuclear dead end, which is iron 56. Iron 56 is special because it has the highest binding energy of any atom. So basically, once you reach that point, you can't fuse higher or fuse any irons to get more energy out of it. It takes energy. It's like an energetic dead end, effectively. And so stars at the end of their life cycle, if they're big enough, can start fusing that stuff. So back to the phases of a star's life cycle, we have 4 phases, right? We have the birth of a star, or this pre-main sequence, in which star formation starts to occur, generally from the consolidation of nebula or planetary nebula or gas clouds, effectively. As that happens, it'll reach a point where it will ignite, and basically hydrogen fusion, that proton-proton one chain reaction, starts occurring in the core. And then you have entered the main sequence. It's now a real star. It's doing its thing, right? Stars will eventually run out of that hydrogen, again, as they convert it to helium. And as they run out of it, they'll start trying to fuse heavier and heavier elements. If they are massive enough to get to that point to fuse heavier elements, it'll enter this post-main phase sequence where it will start to get basically hotter and fuse heavier and heavier elements until it reaches that nuclear dead end, or it's just not massive enough to fuse heavier elements. And then eventually, once it's entirely out of fuel, you'll reach that death and collapse where basically fuel runs out and basically the star dies, leaving behind some kind of remnant. Right, so now let's talk about the formation of stars. Right, so effectively all star formation starts from a giant cloud of dust. These can be the remains of previous stars, as well as just gas material left over from the Big Bang. There we go. Right, so as these gas clouds start collapsing, they'll basically transfer their gravitational energy or potential energy into heat, and they start getting hotter. And basically, as more and more mass accrues, they get hotter, and there's more pressure in the center. And this basically will start the formation of something known as a protostar. Right. Right. So protostars are very young stars. They're still gathering mass. They're just starting. They're little baby stars. And basically, as they start accruing more and more mass, their heat and pressure in their cores will start increasing. The temperature or the heat from these stars come not from fusion yet, but from consolidation of matter. The pressure in the stars basically is heating it up. And once it reaches a critical point of around 10 million Kelvin, that is when proton-proton chain reaction will be initiated, and it would be a real stars, and they start a fusion of hydrogen to form helium. But if there isn't enough star for a mass to get to that point of 10 million Kelvin, you'll get something called a brown dwarf. This is basically the failure of a star to form. It's these bodies between 1 to 7% solar mass or mass of the sun. So they're still massive, big things, but they just don't have enough mass to consolidate the core to get to the 10 million Kelvin point. And so they'll fuse, sometimes they can fuse elements that are easier to fuse, like deuterium and lithium, but generally they'll be very dim, not very bright, and it's very sad. But now we'll get to stars that have entered the main sequence. So this is the Hertzsprung-Russell diagram. It's basically a scatter plot of the luminosity or the brightness of a star and its temperature. And you can see there is a definite link. At the bottom right corner, you can see there's stars that are very dim, very low temperature. And as you heat the star up, as the star gets more massive, it gets hotter. And as it gets hotter, it gets brighter. We can also see several different populations here. So you have, right, your main sequence, all those stars, that purple line going up from basically the bottom corner up to the top. Those are stars that are burning hydrogen. And then you also have different populations too. I don't know if you can see, but there's at the top right, there's the giant, supergiant categories. These are stars that have basically run out of hydrogen and moved over to fusing different elements. Right. And then also there's white dwarfs, which are stellar remnants that we will go into more detail in the next few slides. Right. So again, as stars fuse, fusion is generating. So basically, stars above this certain 0.4 solar masses will fuse heavier elements and will enter a giant phase. Right. So as hydrogen fuel runs out, the radiation pressure that's generated from the heat of the core and from that fusion taking place is basically counteracting the force of gravity. Right, because gravity wants to crush it all down as small and tight as possible. But that radiation pressure from fusion is basically balancing it out. So when you run out of fuel, basically that radiation pressure decreases and gravity contracts further on the star. And that basically makes that central core hotter. And as it gets hotter, it's able to fuse heavier elements, and the radiation pressure basically jumps up and counteracts gravity. So what will happen is you'll have cores of stars that are entering or running out of fuel, basically expanding or getting hotter and hotter. And then this will actually results in the star actually getting larger. Basically, the top layers expand from the heat. You'll actually get a cooling star, which is a very interesting process. So that is that. And here's again that same Hertzsprung-Russell diagram. And here you can actually see lines tracing how the stars change over time. Generally, for lower mass, for all stars, you'll see they start basically getting that cooling effect, leaving the main sequence. Some of them that are more massive have a lot more stages and a lot more weird things happening, but generally they move to the right as they get dimmer on the surface, but hotter in the core. And that's them entering their giant phases. Basically, the bigger the star, the shorter the lifespan. So high mass stars, again, like 120 times the mass of our sun, this is on the edge of big, as big as they can get. Those will last for a few million years, and the lowest mass stars can last as long as trillions of years, which is an incredibly long time. So now we're reaching the end. For the largest of stars, you'll have interesting things like this, where you'll get layers of materials as density gradients form. You'll have basically cores of the heaviest elements, iron, and then as they go out, you get lighter and lighter elements, and you'll have fusion occurring on these layers, like kind of like an onion. This is generally the last moments of a star's life, and basically it looks like this for a very short time before it dies, and they can die in quite a variety of ways. Okay. So once your death happens, you're out of fuel, you have nothing left. Oh no, that pressure, basically that radiation pressure isn't being generated anymore, and so gravity is going to take hold, right? So basically, if a star is massive enough, you can have supernova. This, I believe, is actually a planetary nova. We'll get into that. And basically, when stars die, they'll leave behind a stellar remnant. It's either going to be a white dwarf, a neutron star, or a black hole. And that remnant it leaves behind is entirely dependent on the initial mass of your star. Right. So basically, for low mass stars, the ones that are just using hydrogen, they're going to live for trillions and trillions of years. There actually hasn't been any observed because their lifespan is longer than the age of the universe. Right? Then you get your mid-sized stars, which are between 0.4 and 7 times the mass of the sun. These will generally expand into the giant phase and leave behind something called a planetary nova and a white dwarf. That's what we saw actually on the previous slide. There, this is the planetary nova. Basically, the outer layers of the star are kind of left, and in the center of that, you have a white dwarf. Right? And then for the largest of stars, for those greater than 8 solar masses, you'll expand to giants using heavier elements, and when they die, they'll die in a supernova and leave behind a stellar remnant that's either a neutron star or a black hole. So we're going to go into what those stellar remnants are. Right? So white dwarf, the stellar remnant for smaller stars, is basically the core of the star that's left over after the formation of planetary nebula. Generally, they're made up of electron degenerate matter, which is a very interesting thing in which basically there's so much stuff pushing down on it, it forces the electrons orbiting the atoms basically into the lowest possible energy state that they can occupy. These generally will be mostly made of oxygen and nitrogen left over from the star's core. Basically, these objects are very dim, they're radiating energy, basically the heat left over from the core, and as they do that, they'll generally get darker and dimmer. They'll eventually form black dwarfs after trillions of years of radiating that leftover energy. Right. And then second one is neutron star, again composed of degenerate neutron matter. This stuff is really interesting because basically what's happening is that there's so much pressure that normally neutron or the electrons, so again, how electrons orbit nucleus, right? There's so much pressure that it's not able to be in that lowest energy state. Instead, it will fuse with protons to form neutrons. So it's basically a material that's entirely made of neutrons. There's additional exotic matters, basically in how they interact. And also they can form something called pulsars, which if they're rotating really quickly, they can release short-timed X-ray and gamma ray bursts, which are really interesting. Cool. Right. And then black holes are the last one, which are really, really cool. So the anatomy of black hole, again, you have here your accretion disk, which is where material falling into the black hole happens. You have your singularity, which is the center point of a black hole. And around that singularity, you have an event horizon, which is basically the point of no return, where if past that point, your escape velocity needs to be greater than the speed of light to escape, and that's impossible due to relativity. So basically anything that enters that point is stuck there. You also have a photon sphere, which is the innermost stable orbit that a photon can orbit around. It's either orbiting there, and any closer, it either has to follow a pathway or space line that leaves the black hole or enters it. So there's different classes of black holes, right? Black holes are formed by, again, the class of stars. So these stellar and intermediate black holes can be ranges of dozens of solar masses to hundreds, even thousands of solar masses. And these black holes generally will be gain mass from either merging with other black holes or feeding on material nearby. Okay. And then supermassive black holes. If you don't know these images were recently taken in astronomy a few years ago, actually. And these are the first actual photographs, visual representations of black holes that we've ever had. And they're really pretty. So these supermassive black holes don't form like normal black holes. Basically, there hasn't been enough time in the life of the universe for them to accrete enough matter to get to the size that they are. These black holes are in the ranges of millions to billions, even trillions of times the mass of the sun. So these are gigantic, with event horizons that can reach literally, you can fit like the entire solar system inside the event horizon. That's how big these things are. And so there's two main theories currently on how they initially formed. One is primordial black holes. So basically at the beginning of the universe, shortly after the Big Bang, there's enough energy and matter in the small localized space to basically create these black holes. And these black holes would be in the range of thousands of times the mass of the sun. Or there's another one in which basically something called a quasi-star black hole, where early in the universe, there was enough mass to form these stars that were basically dense cores that were dense enough to turn into black holes. And basically they were being forced by the star mass around them. Another interesting observation of supermassive black holes is they're found at the center of most, if not every galaxy. And at least an interesting question on if they're required for galaxy formation or if galaxy formation leads to supermassive black holes.
So we don't know why it's black holes originally like created.
Yeah, so
because like they condense, it suddenly like to condense in the middle like.
So for stellar black holes, basically that's what's happening. You have the core of the star. Basically, once you run out of fuel, it's so massive and it's dense enough that basically it collapses into that black hole, which is what causes supernova. Is that collapse of the core basically throws out all the other layers of the star, and that's how you get that. So that's how these formed. But because for supermassive black holes, there isn't enough time in the universe for them to have been fed to get to the size they were, so they couldn't have formed by normal star core collapse. They had to form from another method, and that's where these two methods come from. And currently, I don't believe there's a lot of evidence for either of them right now, as far as people aware of. But yeah.
Have they ever like seen what's like sense of like
No.
back?
Yeah, so yeah, once you reach that point, you can't come back. So like if you did send one in, right, the radio signal that it sends out can't get out of that, can't escape it basically. The escape velocity of inside that point is greater than the speed of light. So anything that passes that point, well, you can't communicate with it. You don't know what's happening.
So you don't know what's on.
Yeah. Yeah, no, we do not. So yeah.
In the movie.
Oh yeah.
He went there, right? He went there.
Yeah, so what would actually happen is actually much more strange. So for those supermassive black holes, the event horizon surface gravity there is so, because they're so massive and extremely heat, the surface gravity there, you probably just enter and there wouldn't be much happening until you start getting closer to singularity, at which point they'll probably be vaporized. Along with a variety of other fun and interesting things, but I don't think you'd be able to communicate the past there. Like the movie.
But how does it affect the perception of time as you approach the event horizon?
Oh, so again, like, for these supermassive black holes, the time dilation is going to be very small at the event horizon. Whereas like supermassive black holes, you'll have pretty significant. So like if you do the calculations for it, at the event horizon, it's not that much because the event horizon is quite away from singularity. Like versus like a planet where you're on the surface, it's like a much bigger shell and so that time perception is going to be as great as like things like on neutron stars and things like that. You actually have greater surface gravity on the surface of neutron star than on the event horizon. So you will have as you fall in, you will experience time dilation, but unless it's a really small one, you won't experience an insane amount of it. Like if you were traveling on neutron star.
We can't get inside of that black hole, so we took this picture. Like,
This isn't the inside. This is the So, with black holes, again, with the event horizon, no light can escape. You can't actually observe it. It's effectively, hence the name, black hole is black. You can't see anything. So basically what we're actually seeing here in these images, can I see the mouse here, right? So you have this material around here. This isn't the black hole. This is that accretion disk of material. Basically, as material is orbiting the black hole and falling in, it bumps with other material, and that generates a lot of heat in the form of light, basically. And so that is what we're actually seeing in these images, is that accretion disk. Now, black holes are even more crazy because due to special and general relativity, light, the path of light can actually be bent. And so because of the gravity of these objects, light is actually lensed from the back. So the reason why you see this really bright ring and then it's dim at the top is this is actually light from behind the black hole that's coming around, lensing from the mass of the black hole. Yeah. So what you're actually seeing here is the interactions or effects of black holes, because you can't observe them directly. If you just had a black hole, nothing else around, you couldn't possibly tell that it was there. What you can see though is the effects, the gravitational effects, things that are orbiting it, which is how we first discovered Sagittarius A star in the center of the Milky Way galaxy. We saw that everything was orbiting this really massive thing in the center of the galaxy. And then here you can see from the material that the black hole is feeding, those accretion disks. Really cool. Yeah, so these are two different black holes. The top one, Sagittarius A star, is the one at the center of our Milky Way. I believe it's around 2 billion solar masses, something in that range. And this one is a different galaxy, elliptical galaxy M87, or Messier 87. This one is a little bit bigger. I think it's closer to 1 billion or so solar masses. In that range.
Solar mass, that's the M with the dot. Right?
Yeah, and with the circle dot, I didn't think I mentioned that, but yes. So basically, it's a standard unit of measurement, generally to give an idea of what the things are.
So we're falling into the.
No.
Vegetarian.
So no. So
It's in the center.
yeah, it's in the center, right?
And then
So,
slowly attract into.
so we are far enough away, and it's not massive enough that we don't interact very much with this gravity. But material that's closer and like the core is basically, yeah, we are all basically orbiting this supermassive black hole, but we aren't falling it. But
It's like the Earth is not falling into the sun.
yeah, thank you, John. That's exactly it. Yeah, we're not falling into the sun. Same thing here. We're orbiting. Any questions? Yeah, that's it.
I got more questions.
Okay.
So like, you know, the life cycle, that's like a bunch of life cycle. Like, how long does it take? Time.
So going back. So again, it depends on the mass of the star. So for low mass stars, here. So, right, so for these main sequence stars, right, it takes about a few million years to get to this point where they enter the main sequence. And once they reach that point, it depends entirely on their mass. Like for these red dwarfs, here, for these really, really small dim stars, these red dwarfs are effectively what they're called. They are fusing very, very slowly, and so they can last trillions of years in the main sequence before they start running out of fuel. Versus stars here, like our sun, which is around this range. Stars here in this range will last about 10 to 20 billion years in the main phase before they die. And then you have stars up here, which are like these super massive stars. Absolutely ginormous stars. Because they're so massive, they fuse faster. And so they last in terms of tens of millions of years.
So, just very basic question. Why they call it stellar?
What do they call it? What?
Stellar, why they name the stellar?
Stellar?
Yeah,
For the black hole? Or?
no, you said that stellar, super, but why they call
Oh,
it
so stellar is just because it comes from stars.
stellar? How much star?
Yeah.
So the beer stellar, they just why they call it stellar?
It's just a word. It's a word.
The word, yeah, the word. So the English word stellar is they come from the star.
Yes.
Okay.
Yeah.
Great.
Probably, there's a good chance it's Greek.
Yeah, so that's why we're curious about the setup here.
I don't think that.
Maybe I drink beer, is that okay?
I don't think there's stars in there. There's a good chance. I put my money if I was a betting man.
It's actually stars are made.
No, I
You
think
see, the company Stella actually gathered material in space to make the stars.
you know, we have drink too much and some stuff.
Unfortunately, astronomy has not observed that.
So you were talking about solar masses, one solar mass is the size of our sun.
Yeah, so it's slightly different because you can use initial stellar mass and current stellar mass. So basically, as stars are living, right, they're fusing hydrogen to helium and that's releasing energy and basically converting the mass of the star to energy. The initial mass of the star is actually going to be higher than what it currently is. Most often than not, they use the current mass of the sun though.
Okay. And then given your research on this, do you have any comments on the myth that like the world is round?
The Earth is the Earth. Okay, this is a common misconception. I want everyone to clear it up. The Earth is not flat; it is hollow, and in the inside, there are
The lizard
secret. Yeah, the lizard people. Yes. Yeah. So, but yes, the Earth is hollow.
the lizard people make Stella.
Exactly. Yeah. All right. Yeah.
Yeah, sorry, I missed the first part of it, but did you talk about the concept of a singularity?
Yeah, so not too much, but yeah, we can go further over that. Like, so if you do field equations for general relativity, for black holes of certain density and masses, you end up with something called singularity. So that is what's thought of to be at the center of the black hole past the event horizon. Yeah, singularities are weird and they break physics and we don't have good models to understand exactly what it is. It's entirely possible there isn't a singularity. There's actually a new state of degenerate matter behind there, but we really don't know. But currently, it's theorized that there is a singularity where basically the mass is basically condensed to a single point in space-time.
Yeah, so basically it's all that mass, but it's not occupying any space as we understand it.
Yeah, as we understand it, it's basically in a single point. So it's effectively infinitely dense point of material.
Hence black hole in
Yeah.
space-time.
Yeah, and that singularity is what's curving space-time. So that's why you see the light. That's why once you reach that point, escape velocity and all this stuff.
Just maybe it's a little bit out of topic. Like we have these black holes. This kind of object constantly get bigger and heavier because it's accumulated all matter around.
Yeah.
So, like theoretically, like initial point for our universe, it was a gigantic black hole.
Yeah, you can think of so again, like this stuff is outside the current model of physics. We don't have current implications of that. But yeah, effectively what happened at the Big Bang was a singularity and it stopped being a singularity.
Yeah, and my question is like why it was explosion of this.
Why?
Yeah, because like it's look like it still will be condensed infinity. Like, and what will be like critical point for explosion? Like how much matter should be reached inside of this single black hole
So
to start new like Big Bang?
So way to think about it is not the singularity itself, but basically an infinite expansion of space-time. There's hidden slides or slides I got rid of that I talked about after the death of all the stars, basically what happens to the universe. But you can think about it not in the accumulation of mass, but in the expansion of space-time. From a single point to so you know how the universe is currently expanding, right? We have negative energy, universe is expanding. So what can happen is you can have localized points of space-time basically generate new space-time. So you can have basically a cascade or chain effect where you take a local point of space-time and it infinitely expands. This is actually something they did a paper on a while ago, and they calculated the approximate time to take space-time for that to happen. And something like 10 to the 10 to the 70 years. So an unbelievably long time for it to happen. But if it did happen, you wouldn't actually be able to see it Because it would be quantumly confined. So it's just really weird stuff, and I'm not smart enough to go into further topic. I don't have a PhD in astrophysics or any physics for that matter. But yeah, that's the layman's term as I understand what's happening.
So in this case, like original point, like why this disclosure? Because it's accumulated too much.
Yeah,
Because there is not too much. It's like an infinity possibility.
yeah.
In this case, it should be like I like listened to a couple video about this, like, and one guy said this is just basically there is no Big Bang because it's like basically there is universe even before explode Big Bang. Like,
Yeah.
in this case, it wasn't a real like final condensed point from which it all exploded.
Yeah, so there's a variety of theories on that, and again, like current understanding of physics don't really work past like the first Planck's length times, like 10 to the negative 30 seconds past the Big Bang. We don't really have a physical or model understanding of what exactly happened at that point, so you can kind of say whatever you want, and no one can really prove you're wrong.
Maybe the reason is the universe only going one direction. Maybe if you observe two directions, then maybe there's no Big Bang. That's like everything going.
Yeah, I'm not physics either. In this case,
Yeah,
for
I
me,
don't think-
it's like
What do we use to find that? Is there a map of like, what do we do?
So for actually finding black holes, there's a few ways you can do it. One of them is you're observing the gravity. So for our black hole, we can observe the effect of other stars orbiting around it. You can also see other effects, basically. One of them is that when black holes are feeding, that accretion disk is happening. It can have something basically where, for rotating black holes, you get a magnetic field that can actually shoot charged particles out of the top of it. You can actually detect those. Those are quasars, or what they're
like
called.
quasars.
Quasars. And so there's like that. You can detect that material is coming out. There's a few other ways, but I'm going to keep on them right now.
Like we use satellites to detect them.
So yeah, so these are done with infrared, I believe. Basically, what you can do is you can make a really big infrared telescope by using observatories all across the Earth, and basically point them at the same space. You effectively have the lens the size of the Earth, the diameter of the Earth, and so that's how I think these were actually photographed. Because they're really dim and really far away, it's really difficult to do. So you need a really big lens effectively over a period of time to actually get that.
I think this might be radio telescope.
Yeah, radio.
It is like, three different places in the.
Yeah, so yeah, you have several observatories at the same time, basically, and as Earth rotates, you have new ones come online and other ones go off. Basically, you can continuously observe a specific point for a long period of time to get this information. Basically, you take all that data and put it into a really cool program that puts out this image.
No, really. So we are in.
Like radar or satellite out there.
No, I don't think any of them are powerful enough to detect make these pictures.
The stars that we see like at night, by the time we see them, they've already died, right?
Yeah, no,
Depends on how-
it depends how far away and what they are, yeah, so actually, most of the stars you see are local, so they are within a few. Most of the stars you can see with the naked eye are local, and they're a few thousand miles away, so generally they're probably still alive. There's a few that may not be, but again, we won't know for thousands of years, there's no, it's really hard to determine. When they die, we'll see them, and we won't know before then if they're dead.
Yeah.
But generally, most of the stars are still that in the night sky are probably still alive. That you can see when you think,
Oh, okay.
How come they're dead?
No, just like with the light years. I don't know.
Okay, no. So you're not wrong. So the speed of light is the limit for how fast things can travel, right? So the photons that have come from the stars are based off how far away they are. So there's 1,000 light years difference between where we are and the star in the sky. The light that we're seeing is like 1,000 years old.
So in this case, whatever we're seeing right now in the sky, it's basically their past.
Yeah,
And like, if we think like when this universe was created, like when we see some like star was exploded because they're too old, it means they're too old in the past.
Yeah,
Yeah.
so when we do see a star die, it's been dead for a while. We just are suddenly getting that information here.
That's also why it's so hard to estimate the size of the universe, because we cannot see beyond like
the
15 billion
yeah
light years.
things get really crazy because it isn't just the it isn't just the distance that light can travel, but it's also the fact that the universe is expanding and its rate of expansion is accelerated. Oh, someone else is here. They're gonna get very interesting. They're gonna get a very interesting conversation here. But where was I?
World expansions.
Oh yeah, so basically, since the universe is expanding, the actual distance or radius of the observable universe is actually bigger. So oftentimes astrophysicists will use something called a redshift scale to determine how far something is away, because the distance can be really confusing. It could be in the distance the light travels, light years, or it can be in the actual physical distance based on spatial expansion. So it can get really confusing, and there's a lot of inaccuracy in that exact measurement. So generally they use something called redshift based on how far shifted the light of that star is.
Most intriguing part for me is like expansion of universe. It's like everywhere at the same time.
Yeah,
There is no like single point from where it's expanded. Like there is no center in the universe. Because
it's everywhere.
it's expanded everywhere equally. Like I think like there's some kind of analogy. It's like balloon.
Yeah.
When you expand, but even for balloon, like you have a center of balloon, like, but how in the universe expand it without center, I just cannot understand. that.
Yeah, so it requires higher dimensional qualities. So like with the balloon example, you're only thinking about a two-dimensional surface.
Yeah.
Expanding, not necessarily from like the balloon inflating, but like if you were on a two-dimensional surface, the like living in 2 dimensions on that surface, it seems like it's all expanding everywhere, everything's expanding. It's the same thing for like a 4-dimensional balloon, and we're living on the 3-dimensional surface of that balloon is what we're observing.
Basically, like in the physics, it's like a lot of things people detect because when they observe something, like in the quantum mechanics, like you can see this only when you observe certain events. If you don't observe these events, it's never happened. And then I'm not sure like if it's just because of like way how we detect these events.
Oh, so you're talking about this quantum thing. Yeah, I know. I know what you're talking about.
Yeah, it means like when we say universe expanded, it's because we observe expansion right now from this point. Like, but who knows? Maybe it's not.
It's based on observation.
Let's say,
The James Webb Space Telescope, the new one, what they're putting up like 2 million now from Earth.
yeah,
So
so
they
it's
can observe the earlier star formation. So they want to observe more.
So part of the reason why the James Space Telescope is so far in the infrared is because it's looking at some of the earliest light that's ever been emitted, and because it's so far away, the Doppler effect has redshifted that light from visible light, basically, or UV to infrared. So yeah, that's part of the reason why we know things are leaving, is because we see the light from these stars are shifted. The spectrometry of these stars are basically redshifted. And you can basically tell how far away they are by how much they've redshifted.
Aside from like the sights, visuals, like what about like the sound, the smell, the taste?
So if you could hear the sun, it would be about 150 decibels. Which is,
So it's not that bad.
that's like jet engine. That's like you sitting next to a jet engine. Is how loud it would be.
So that's all the wind.
Yeah. But yeah, you can't hear the sound because the vacuum of space, sound can't be transmitted through vacuum. But you do get things like solar particles that get ejected from the sun through like solar mass ejections, corona, and things like that. As for star, you'll probably vaporize far before you get close to it. But it's basically just helium or hydrogen.
They need to send a approach to some.
There's some that are really close to it. There's one that was launched a few years ago. That basically has this giant sun shield and it's has these like camera on probes are basically pushbacks and they get really good pictures of the sun. Here's the name of that machine. But yeah, I don't think they send any into the sun. That's really difficult to do. And it's actually harder to send things. Yeah, it's actually harder to send things into the sun than it is to throw them out of the solar system. Which is interesting, yeah. Any other questions? Nope. No, okay, we're done.
Thank you. Great. Let's play over either lunch. Enjoy. We have a cake too. Huh? Okay. Joseph, come down. Come to eat your cake, your birthday.
You ordered the highlights.